I would now like to talk about potential energy in a capacitor. This subject has a lot of practical importance. It turns out that you can have dust explosions. This might occur in the cosmetics industry, or you can get a fire started when a patient is being moved off a gurney. So understanding capacitance and potential energy is important for these kinds of subjects. The textbook has a write-up about each one of these. So let's start with a capacitor. Here we go, and the top plate is positively charged and the bottom plate's negatively charged. And then there's some kind of voltage between the plates. And it turns out this system contains potential energy. And the way you can think about it is as follows. So take two plates which are initially uncharged. In other words, there's zero charge on either plate. And intuitively, what you want to do is think about moving a little charge, dq, from the bottom plate to the top plate. So you're going to move a tiny bit of positive charge from the bottom plate to the top plate, making the top plate a little bit positively charged. And then you keep repeating that process, moving a dq every time, and then eventually the top plate will become totally charged with a charge plus q. So now let's think about how much work is being done to move the little charge. So initially when the plate's uncharged and you move the dq from the bottom to the top, the little dq doesn't feel any force in order to be moved up to the top. So there's no work required to push the charge up. But now when you try to take the second bit of charge and move it up, now you have a positively charged top plate and a little positive charge that's being pushed up. And there's going to be a repulsive force, so there has to be work done by my hand in order to move the little dq up. And the problem just becomes more extreme when you try to move another bit of charge up, because now the top plate is even more positively charged and the repulsive force is stronger. So basically it takes work in order to charge the top plate. And throughout this process, the bottom plate becomes negatively charged. So there's a way that we can write this mathematically. We go back to the original definition of delta V. So that we wrote before, delta V equals minus the work done by the electric field over Q. And then we said that the electric force is conservative. So you can rewrite negative W electric as a change in potential energy. So that's what this says. So you have delta V equals delta U over Q. Now for this problem, I'd like to rearrange it like so. And then what I want to do is try to write an equation that describes how a little bit of charge is moved from the bottom plate to the top plate. So the way I'll do it is like this. I take a little bit of charge dq, and then the work done is, if I have this dq in the presence of a certain amount of potential difference between the plates, it's delta V. And so that's the amount of work done to move the little dq from one potential to the other. This is the work that I do. Okay, now I have to repeat this process many times. So it turns out it's a little bit more convenient to rewrite the delta V. So recall this formula. We know that Q equals CV. Now, in this formula, Q equals CV really means Q equals C delta V. So therefore, delta V equals Q over C. So I'm going to rewrite the thing above, dQ delta V, as being dq times q over c. And that's the work I do. Okay, now we have to do this a lot, so basically you're going to add up many maneuvers of this type, and to add up so many of them, you're basically doing an integral of dq times q over c from the time when q is 0 on the top plate to the time when q is big Q on the top plate. And this is going to equal the change in potential energy. And so it's easy to do this integral. So that's going to come out to be 1/2 q squared over c evaluated from 0 to q, which is equal to 1/2 big Q squared over c, and that equals delta U. Now the delta U means U final minus U initial, but U initial is 0. Okay, so summarizing all of that more compactly, you have U equals 1/2 Q squared over C. This is the potential energy of a capacitor.